All right. Sorry. I apologize for the silly joke. Um, I think we're all losing it a little, but we'll just keep going. So, Newton's laws and systems of object. So, up until now, we've only looked at one object. So, what we want to do now is we want to look at what if there are multiple objects? What if one object is pushing another? And that's kind of where we're going for the rest of this unit. So, Newton's laws. We know Newton's laws. An object at rest or in uniform motion will remain in that state of rest or motion unless acted on by an external force. That's that whole inertia idea. F equals ma, force is mass times acceleration. And there's Newton's third, that for every action, there's an equal and opposite reaction. We always forget to put, there's actually, you should put the word force after that. It's every time there's an action force, the object you're pushing on pushes back with exactly the same amount of force that you push forward on. So, we know the first two pretty well, so I'm just going to sort of skip over that. Newton's third is the tricky one because we don't think that makes sense. Like if I'm throwing a ball, you don't think the ball is putting the same force back on me that I'm putting on it, but it actually is. Even though the ball's accelerating forward, it's putting the same force back that I'm pushing forward. You can't push on something without it pushing back. All right? So how do we figure that out? Well, the way you do that is you look at each object independently. So the reason you don't notice it on me is I'm much bigger than this ball. So the force I'm putting on it isn't enough to actually give me any sort, really change my motion that much. But for the ball, it's much lighter, so you get more of an effect on the ball. So when we do this, like for example, if you're looking at two people on ice skates pushing away at each other, for this person, the only force affecting them is person B pushing back. For this person, the only force affecting them is person A pushing back. So, in fact, it doesn't matter even. You can't actually tell who actually did the push because if they did it, because it will always be exactly the same. If person A pushes on person B with 10 newtons, you'll get 10 newtons back on A, 10 newtons forward on B. If person B pushes on person A with 10 newtons, you'll get 10 newtons in that direction on A, 10 newtons in that direction on B. And it actually doesn't matter who does the pushing because when we look at an object, you only look at the force acting on that object. That's the only thing that affects its motion. The fact that it's exerting a force on someone else has no effect on its motion at all other than that Newton's third law, force. So, here's a typical question, and I want to show you a trick. So this is one of the most common questions you're going to see is you're going to get two weights on a pulley, and under gravity, we're going to say which one goes up, which one goes down. Now, why that's confusing is down isn't the positive direction for both things, right? For this one, up is the positive direction, but if this one's going up, this one's going down, and I can't use down as a positive or negative. It really confuses things. So what's much easier is if you actually, again, do the tilt the world, and instead of drawing it like this, draw it like this. And then when you're done, go back and look at it like this. So draw it like this and say, okay, we got Mr. Cudmore on the one rope. We're going to call Mr. Cudmore's the positive direction. We're going to call Lauren the negative direction. Okay? And we got 165. Well, what forces are acting on them by themselves? Well, Mr. Cudmore, there's the force of gravity is pulling him this way. For Lauren, the force of gravity is pulling her that way. So, Mr. Cudmore has a force equal to mg, which is 981 newtons, just mass times 9.81. This vector that's pulling on her is 638. We'll call that minus. Now, because the rope isn't stretching, it's not breaking, we know that whatever one object is doing, the other object is doing. So this whole thing has to be accelerating in one direction at the same time. They're connected together. You can treat them as one object. So you could treat them assuming the rope doesn't weigh anything, which in physics we have magical ropes that don't, you could treat this as one object that's 165 kilograms with two forces pulling on it in each direction. Then it's really easy to find our net force. We just add the forces, plug it into F equals ma, we find our acceleration, and then we say, well, logically, okay then, Mr. Cudmore is the positive direction, so that's 2.1, so whatever direction he's moving in, that's positive. So Mr. Cudmore will be going down at 2.1, Lauren will be going up at 2.1 meters per second. So one thing I really recommend, whenever you've got a question where there's a weird direction like this, straighten it out. Another trick, one of the most famous questions in physics, a locomotive with a whole bunch of cars, what's the force between two different cars? Now, the trick to this is don't treat the train as 21 things. Treat it as one train with the mass that everything has. So for the first part, what force does the locomotive need to provide? Well, if we add up the locomotive and 20 cars, you have a train that has a mass of 320,000 kilograms. There are two forces. There's the force of the engine and the force of friction. So we can solve that and figure it out, what the force the engine must put. All right? Don't overthink it. Don't try to go, oh my God, well, what's the force in the first, the second, the third train car? Treat it as one train. Similarly, if I wanted to find the force between the 13th and 14th car, the only thing pulling that 14th car forward is the force of the 13th car acting on it. The only thing pulling it back is the force of friction on all the cars. So treat the 14th car back to the end of the train as one object. Add up their masses, figure out, in this case, by the way, Fn does equal Fg, figure out the force of friction on a mass of 105,000 kilograms, figure out the applied force, just because the net force has to be 0 to keep it moving. There's your Fa. Now, what does that mean? Well, that means that the 13th car is pulling forward on the 14th car with a force equal to this. By the way, I apologize, there should be an extra 0. I will fix that on the PowerPoint momentarily. The 14th car is pulling back on the 13th car with this much force. So you don't overthink systems of forces, okay? If you look at it, if you're trying to find acceleration, look at it as one object. If you're trying to find, because only forces acting on that object can affect it. So the trick to this is breaking it up and reorganizing it. By the way, I am going to ask you a reasonably tricky question on this that's going to require you to do something like this, but with one of them being on a slope. And again, here's the trick. Just straighten it out. You'll just have your FG triangle there. That'll be what is pulling the object. All right. Good luck.